Hello everybody, welcome to chapter 6 where we'll be discussing about the basic hardware components that are needed to build a processor from scratch. So what we have done up till now in the last few chapters is that we have looked at what bits can do, how do we use bits to represent integers, numbers, pieces of text. Then we have looked at three kinds of assembly languages in chapters 3, 4 and 5. The basic simple RISC assembly language, ARM assembly and x86 assembly. Now given the fact that we have a decent idea of what assembly languages are, we want to build an actual processor. So to build an actual processor, what we would be discussing in this chapter is essentially the building blocks of actual processors. So I want to repeat once again that this is chapter 6 of the book Computer Organization and Architecture. This has been published by McGraw-Hill in 2015. So let me start with an outline of this chapter. So this chapter is divided into 4 sections. The first section discusses the most basic building blocks of circuits, which are transistors and logic gates. Then we discuss combinational logic, which is basically creates larger circuits by combining these basic elements, which are logic gates. Subsequently, we shall discuss sequential logic. So in sequential logic, we store individual bits, and then we use these individual bits in circuits. Finally, we'll discuss SRAM and DRAM cells. So these are the memory elements inside a processor. We can store data here. We can store bits and bytes. So SRAMs and DRAMs are two very different technologies. So we'll discuss both of these in the last part of this chapter. Alright, so let me start with a disclaimer that this chapter we are providing a very high level overview. So pretty much the entire digital logic course is being covered in this one single chapter. So it might be difficult for some readers or listeners to follow exactly all of that is being said. So the assumption is that at least students have some background in logic gates, transistors, combinational and sequential logic. So then this chapter you can recapitulate all of those concepts and also get a high level picture of all the elements that we need from the point of view of designing a processor. So for a deeper understanding, if it is required, the students can consult any of the classic textbooks on digital logic. Alright, so let's take a look at the basic atom of a circuit, right? The most simplest and it's like an atom and molecule of a circuit. So the most basic element is a transistor. So the transistor in common man's words is basically a switch. So it's the same as a light switch and it's any kind of switch. So when the switch is open, current is not flowing, and when the switch closes, there is a flow of current. So this is as simple as that. When the switch is on, the current can flow from this terminal to this terminal. And if the switch is off, there is no current flow. So the transistor works like an open circuit. So this is the most basic element of a circuit. It's just a simple switch. And how is a transistor made? So transistor previously was being made with different technologies, but for the last 40-50 years, it is being made of silicon. So silicon is a basic element of sand. It's a brownish, grayish material. It is a semiconductor, which means that it's not a conductor and it's not an insulator. It lies in the middle. It is so the fantastic thing about silicon is that it is possible to change its properties. We can add a little bit of impurities to silicon, and this process is called doping. So what is doping again? It is the process of adding a little bit of impurities to silicon. Once this is done, we can change its properties. For example, if we dope it with group 3 elements of the periodic table, such that boron, aluminum or gallium, so then it will become a p-type semiconductor, p for positive in that sense. And So then in this case, the conductivity of the semiconductor will actually increase. So we'll discuss how, but the basic idea here is that if we dope silicon with another element, in this case a group 3 element of the periodic table, its conductivity will increase, and so there is a so there are ways to control that. Similarly, if we dope it with group 5 elements of the periodic table, which are like phosphorus and arsenic, it is called an N-type semiconductor. So recall that in the periodic table, in the outermost band, is in the silicon has 4 electrons, group 3 elements will have 3 electrons, and group 5 elements will have 5 electrons. So how is silicon, so how is a typical silicon, uh, a piece of silicon organized in terms of its basic atoms? So well, so silicon is a group 4 element, so it has 4 electrons in its outermost layer. Similarly, other silicon atoms also have 4 electrons. So essentially 4 plus 4 becomes 8, and so they form these covalent kind of bonds here, and so they arrange themselves in a lattice. So this is a 2D view of what is otherwise a 3D lattice, but you can sort of think that each silicon, conceptually you can think that each silicon atom is connected to 4 other silicon atoms, and so they form covalent bonds of the way that is shown to ensure that they have a stable structure. Now, what we can do is that let us assume that we replace a silicon atom with a boron atom. So, a boron atom is a group 3 atom, right? So, it has 3 electrons in its outermost layer or orbit, and so basically there is 1 electron missing. So, whereas silicon has 4 electrons. So what happens is that inside the lattice, there is a hole over here. So what does a hole mean? A hole essentially means the lack of an electron, right? So basically an electron is not present. So this is called a hole. So, so this is essentially a lack of an electron or one less electron being is a hole. And the reason the hole is there because we have a small boron atom. So the interesting thing is that in this case, holes can actually flow in the sense that this electron can get transferred over here and the hole can get transferred over here. Similarly, holes can also flow like this, that the hole gets transferred over here and an electron from there comes here. So the reason that this happens is that inside the atomic world, things are fairly complicated. So atoms are connected to each other, and so actually, one reason that metals are very heavy conductors is basically because the electrons form what is called an electron glass. Electrons form what is called an electron gas or an electron cloud, in the sense that all of the electrons are available to sort of carry charge or carry current. So in this case, the electrons, it is true that they are associated with atoms, but they are also somewhat mobile in the sense that they can flow. So if an electron flows in one direction to cover up a hole, conceptually we can think that the hole is flowing in the other direction. So the hole per se is not a physical quantity, it is a lack of an electron. But we can conceptually think of a hole as a charge carrier, where it is associated with positive charge, and the fact that the hole moves, let's say in this case, from the right to the left essentially means that an electron moves to fill up the hole from the left to the right. So the holes are considered as charge carriers. If you take a course on device physics, you will study a lot about electrons and holes and compute effective masses of holes and so on. But for the sake of an overview, these advanced concepts are not required. The only thing that needs to be understood is that a hole indicates the lack of an electron, and the hole itself can flow. For example, if I apply, let's say, a strong negative charge, that will essentially repel electrons away from it. So basically the hole can then flow towards the negative terminal, which essentially means electrons are flowing in the other direction and the hole is flowing towards the negative terminal. So the hole we can think is that it is conceptually associated with positive charge. Similarly, we can have another kind of doping. Okay, there's this animation over here, so let me show this once again. Let us consider the hole that was created by adding the boron atom, and let's consider an electron. So if we apply a strong negative potential over here, then electrons will get repelled from the negative potential, and thus an electron will take over a hole and the holes can migrate towards the negative terminal. So we are thinking of a hole as a net carrier of positive charge, and it essentially can move, so it is associated with current. So let us now look at a similar kind of doping called N-type doping, which is actually the reverse of doping with group 3 elements. In this case, we are doping with group 5 elements. So let us assume that there is a phosphorus atom in the lattice. So it will create bonds with the rest of the atoms, which is fine, but it will have one extra electron. So this extra electron that is there can essentially migrate and carry current. So these electrons will flow, it is associated with a net negative charge. So let us show a similar example that electrons on the application of an electric field, which is essentially a potential difference, electrons can flow right from the negative end to the positive terminal. All right. So at this point, what are the two important concepts that we have read? We have read the concept of a hole, which is a lack of an electron, but conceptually it can be thought to carry positive charge. And then we have studied about an electron. Electron carries negative charge. So how is a hole introduced? A hole is introduced when you dope silicon with a group 3 element. So in that case, one electron is missing, as you can see from the previous slide. One electron is missing from the lattice, so that creates a hole, and the hole can migrate and electrons can come and fill it up. So basically the hole in this case is thus associated with positive charge. Similarly, in this case, we'll have an extra electron which can migrate within the lattice, and it will migrate towards the positive terminal as is shown in the animation over here, and thus it can carry current. This is precisely the reason why if we dope silicon with with either a group 3 element or a group 5 element, we have extra charge carriers. And what are the extra charge carriers? They are either holes or they are electrons, and thus the net conductivity increases. So with this basic understanding of p-type and n-type semiconductors. So what are n-type? N-type semiconductors are semiconductors doped with group 5 elements like phosphorus, and p-type semiconductors are is silicon essentially doped with group 3 elements, which is boron. So let us make a simple transistor. So let us consider an n-type well, and in that put two smaller wells of p-type material as is shown. Then let's have a metallic contact, and let's call this terminal the source. This is called the source. Let's call this the drain. And then let's put a layer of silicon dioxide, which is an insulator, which is a very strong insulator in fact. Silicon dioxide is regular sand. So you put a layer of silicon dioxide and then a conductor on top of it, which is typically polysilicon, but it's not necessary that it's polysilicon. It can be a metal as well, but doesn't matter. One sec. So it's typically a polysilicon layer which is a conductor, and on top of that we attach a metallic wire, and this terminal is called a gate. So a basic transistor has two terminals, has three terminals. One of them is the gate, one is the source, one is the drain. So this is called an NMOS transistor. So in NMOS, so N stands for the negative, the fact that it's an N-type substrate, and so basically the MOS transistor over here, how do we do? We put two P-type wells in an N-type substrate. So now let us assume that we apply positive charge to the gate. If we apply positive charge to the gate, what will happen? Right, so let's assume that there is positive charge to the gate. So what will happen is that all the electrons will start migrating towards the gate. So in this case, a channel will form, a channel of electrons. So this will form because all the electrons will migrate towards positive charge. And the channel over here, which is rich with electrons, is a conducting channel because it has a lot of charge carriers. So it will be a conducting channel, so it will be possible to actually pass current from the drain to the source via the channel. Right, so that is a possibility. And so thus the transistor, in this case, the switch will in a sense close. So basically current can flow. Then if we apply a negative or zero voltage to the gate, the channel will go away. And since even a doped semiconductor is not a very good conductor of electricity, we can think of this as the switch being open. So what is the controller of the switch? The controller of the switch is the potential at the gate. If we apply a positive voltage at the gate, all the electrons will get attracted towards the gate, and they will get accumulated over here because they can't move further. This is because of the SiO2 insulator that is over here, the black box. But they will accumulate here and they'll form the channel. And then if let's say we apply a positive charge at the drain and let's say connect the source to the ground, it is possible for current to flow across the channel. And the reason it is possible is that because the channel has an excess of charge carriers and which can conduct current. So in this case the switch is closed. But now if we apply a negative or a zero voltage, right, let me write negative or a zero voltage to the gate, the channel will vanish, it will break down, and the transistor will not remain a good conductor. So this is a very, very high level 20,000 feet kind of view of what a transistor does, right? So essentially a transistor is a switch. And so if you consider any mechanical switch, how does it work? We essentially press it with our finger. So in this case, we don't press it with our finger because the transistor is typically a very small structure. So nowadays the transistor is typically 16 nanometers or 14 nanometers, right? Very, very small structures. So instead we apply a voltage at the gate. If it's a positive voltage, in the case of an NMOS transistor, the transistor will conduct. Otherwise the transistor will not conduct current. So the symbol for an NMOS transistor is like this, that this is the symbol, this is the gate over here, and then we have two terminals, the source and the drain, which are interchangeable. The most important point to note is that if we apply a positive voltage at the gate, the transistor will conduct, so it will become like a single wire with a resistance, of course. And if we apply a negative or zero voltage at the gate, the transistor is off, so no current will flow across it, right? So apply a positive voltage, current flows from the drain to source. Apply a zero or a negative voltage, there is no current flow. Now let's take a look at the reverse, a PMOS transistor. In this case, inside a P-type well, we have two N-type smaller wells, right? Or actually this is not called a well, it's called a substrate. So inside a P-type substrate, we have two N-type wells. So in this case, the control is actually reverse. So if you apply a zero or a negative charge to the gate, what will happen is that all the holes will get, so let's say I apply a negative voltage to the gate, or even if there is no voltage, and so what will still happen is that I can design the transistor in such a way that if there is a small negative voltage, or even if the voltage is 0, all the holes will get deposited here, just below the the SiO2 layer. So the structure is the same. So here is what I can do. So let us assume that I apply a positive charge to the drain, right? And in this case, let me assume that the gate in this case is connected to the ground. So what will happen is that if you consider, let's say, this region of the transistor, so in this case there is a net positive charge, and here let's say the charge is 0. So what will happen is that because of the positive charge, all the holes will get repelled, and they will essentially try to move towards the top, which is the gate. They will not be able to go because the SiO2 layer is there, but they'll essentially get stuck over here at the boundary. So we'll have an excess of holes over here, right? So we'll have less holes here, but we'll have more holes towards the n type, but nevertheless there'll be some holes over here. So we'll have a lot of charge carriers in this region, mainly because there is a potential difference, right? And holes will sort of get repelled from the positive regions and move towards wherever they see a lesser voltage, and the lesser voltage is at the gate, so all the holes will try to move towards the gate, and they will accumulate in this region and they'll form a channel. Alright, so this part is the channel. After that, we can have a stable current flow across the channel. So the switching of a PMOS transistor is the exact opposite of an NMOS transistor. In a PMOS transistor, the channel gets formed when the voltage at the gate is either 0 volts or the voltage is negative, and this is when the transistor conducts. If we now apply a positive voltage at the gate, what will happen is that all the holes will get repelled away from it and the channel will pretty much die. Once there is no channel, there are no charge carriers in this region, hence current will not flow. Now let's take a look at the symbol of the PMOS transistor. So it is more or less the same as that of an NMOS transistor, with one simple difference. So the difference is the circle over here at the gate terminal. So that's mainly the only difference. Otherwise, the rest of the diagram is the same, and we have two terminals, the drain and the source, which are interchangeable terminals. And in this switch, if we apply a 0 or negative voltage, the transistor conducts, the current flows from the drain to source. And if we apply a positive voltage at the gate, the transistor is off, there is no current flow. So let me at the end summarize our discussion. So we have two kinds of transistors, an NMOS transistor and a PMOS. So N basically stands for an N-type substrate where there are two P-type wells. So an NMOS transistor, what is MOS? It is metal oxide semiconductor. The reason being that we have all three here. We have a semiconductor substrate, we have an oxide layer, a silicon dioxide layer, which is the insulator on the gate, and we have metallic contacts to the transistor. So we have a metal, oxide and semiconductor. So the NMOS transistor, whose symbol is like this, is basically controlled by the voltage at the gate. If it's positive, current flows, otherwise it doesn't flow, right? And the PMOS transistor, the symbol is more or less the same. It's just that we have a circle over here. So it has a reverse operation. So if the voltage at the gate is either 0 volts, either the gate is grounded or it has a negative voltage, in this case current does not flow across the transistor. So current flows across the transistor, and if the gate has a positive voltage, then current does not flow across the transistor. So we have two switches, two different kinds of switches with different modes of operation. So let's use these transistors. What good is knowledge without actually using it? So let's use it to make an inverter. So this is the sign of an inverter. So what it does is that if I apply a logical 0, then the output is a logical 1. And so the logical 0 might physically correspond to 0 volts, and a logical 1 might correspond to 1 volts or 2 volts or 3 volts, that is immaterial. Then if I apply a logical 1, then at the end I get a logical 0. So it pretty much computes the complement of a bit. So how do we do it? So let's assume that I send in a logical variable A, which can be 0 or 1, and I have an NMOS transistor T1 and a PMOS transistor T2. The PMOS transistor is connected to the supply voltage VCC at the top, and the NMOS transistor at the bottom is connected to ground, and the output is from is basically at this terminal in the middle, right, of the diagram. So let's first see if I apply, if A is equal to 1, if it's a positive voltage, what happens? In this case, if it's positive, T1 will conduct, right? T1 will conduct and T2 will not conduct. So effectively, this terminal will get connected to ground. So if the value here is 1, the value here, since it's connected to ground, will become 0. So it effectively works as an inverter. Similarly, let's take a look at the other case where A is equal to 0 or 0 voltage. So in the other case, what will happen is that the transistor at the bottom T1 will not conduct, right? But the transistor T2 will conduct, and this output will be connected to VCC. So then it will become a logical 1. Alright, so if I have a logical 1 here, the output is a logical 0, and if I have logical 0 as the input, the output is a logical 1. So this acts as an inverter. So this kind of a circuit is a combined NMOS PMOS circuit. So it's called a CMOS circuit, and so it's a combined circuit, right? It has both NMOS elements and PMOS elements. But the important thing is that we put NMOS and PMOS in series, and one end of NMOS is at the ground and one is at VCC. And all that you need to do to understand the operation of such circuits is basically consider pairs of inputs. So if the input is a logical 1, then you need to find out which transistors are on and which are off. So in the case of logical 1, this T1 is on and T2 is off. So the output gets connected to ground, hence it is 0. So let's see more examples of a similar logic. So let's consider a NOR gate, which is of the same type at least. So it looks similar, but we have twice the number of transistors. So let's find out what it does. So a NOR gate is actually, so let's first take a look at the NOR function. So we know an OR function, which is A or B. So an OR function is essentially the logical complement of A or B. So let's consider the combinations of values. So for 0 and 0, 0 or 0 is 0. So the NOR of 0 and 0 is the NOT of 0, which is the logical 1. For all the other combinations of A and B, which are 1, 0, 0, 1 and 1, 1, A or B is equal to 1 and its complement is 0. So that's the reason all three of these values are zeros. So this is exactly what we want to compute via these 4 transistors. So let's see the organization. So we have 4 transistors named T1, T2, T3 and T4. The input A is connected to T1 and T3. The input B is connected to T2 and T4. So T1 and T2 are connected in parallel and T3 and T4 are connected in series. So T1, T2 are NMOS transistors and T3 and T4 are PMOS transistors. So let us first consider the simple case where A is 0 and B is 0. So in this case, both the NMOS transistors are off. So T1 and T2 are off. And both the PMOS transistors T3 and T4 are on. So the transistors are on. This basically means that T3 and T4 form a conducting path. So the voltage at the output terminal out will be the same as VCC or the supply voltage, right? So the voltage at the out terminal will be the same as VCC, the supply voltage, because T3 and T4 are conducting. So hence that will be a logical 1. Now let's consider the next situation where A is 1 and B is 0. So if A is 1, the transistor T1 will conduct. So as a result, it is on. Since B is 0, T2 will be off. So as a result, it is off. Similarly, let's take a look at T3 and T4. So since A is 1, a logical 1, it's a high voltage, T3 is turned off. And T4 will be turned on, but it doesn't matter. So the reason it doesn't matter is because when transistors are connected in series, if one of them is off, the entire line is off. But what we have over here for this, for the second input, is that the transistor T1 is conducting, so the output terminal is directly connected to ground. Because this transistor T1 is conducting, so essentially we can sort of add a straight line over here that it is directly connected to ground. As a result, the voltage at the output terminal is equal to the ground voltage, which is 0, and thus the output is a logical 0. Similarly, we can consider the other pair. It's an absolutely symmetric argument here for 0, 1. So in this case, when A is 0 and B is 1, you can see that, so this is basically T1 is off, T2 is on, T3 is on, and T4 is off. The important point to note that in this T3 T4 pair, in this case T4 is off. So as a result, the supply is not connected with the output line. But out of T1 and T2, T2 is on. So in this case, this has become a closed circuit. So as a result, the output terminal is connected to the ground via T2 and its voltage is 0. Similarly, if both A and B are 1 and 1, then both T1 and T2 are conducting. So both of these lines, the outputs are connected to the inputs. So the output terminal is connected to the ground, and since the ground represents 0 volts, the voltage at the output terminal is 0. So what we get to see over here is that using a CMOS logic, we can create with NMOS and PMOS transistors a structure via which we can compute A NOR B, which is essentially A or B complement, and this is the symbol of the NOR gate. So this, which is a regular OR gate and a circle. So the circle denotes inversion. So a regular OR gate would be a gate like this, right? A and B, two terminals. So if we add a circle, it becomes A NOR B, which is the complement of A or B. So let us now take a look at the NAND gate. The NAND gate is the same thing as NOR, essentially conceptually the same thing, where we compute A and B and we take a logical complement of this. So this becomes A NAND B. So here what we have is that we have a similar looking design, very different though if we start taking a look at the details. So we have the NMOS transistors in series, T1 and T2, and we have the PMOS transistors in parallel. So the input A is connected to T1 as well as to T3, and the input B is connected to T2 as well as to T4. Alright? And this is the symbol of an AND gate, so which is basically an AND gate plus a circuit. So had I drawn the gate symbol as this would have indicated A and B. But if I draw a circle over here, it indicates A NAND B. NAND basically means I compute the logical AND between A and B, and then I take the complement. So that is A and B complement. So what I can do now is that let's take a look at all combinations of A and B and how this circuit works. So if A is 0 and B is 0, both T1 and T2 are off, but T3 and T4, both of them are connected, are on. So basically the voltage at the output terminal will be the same as that in VCC. So as you see, the output voltage is 1. So let's consider the case where A is 1 and B is 0. So if A is 1, then transistor T1 is conducting, but transistor T2 is off. So as we had mentioned in the last slide, when two transistors are connected in series, if one of them is turned off, essentially current is not going to flow via that line. So basically we can sort of assume that the output terminal is disconnected from the ground. But let's take a look at T3 and T4. That's more interesting. Since A is 1, T3 is turned off. But since B is 0, T4 is turned on. Hence we have a conducting path between the supply voltage via T4 to the output terminal, right? So basically current can flow like this. As a result, what can happen is that the voltage here will get set to the same voltage, a similar, roughly similar voltage as the supply voltage, and we can assume that it's a logical 1. So I'll not be describing the other symmetric case here where A is 0 and B is 1, but the logic is very similar. So in this case also the output is a logical 1. Let us now consider the case where A is 1 and B is 1. That's important because that's when A and B is 1, so A and B has to be 0. So if A is 1 and B is 1, the transistor T1 conducts and transistor T2 also conducts. So essentially you have a straight path between the output to the ground. What about T3 and T4? Both of them are turned off because the voltages at A and B are 1 each. So what we see is that in this case the output will be driven to a logical 0 because it is directly connected to ground, which is assumed to be at 0 volts. So this is the operation of the NAND gate, which is very different from that of the OR gate. I'm sorry, the NOR gate. But the important take home point is that we are connecting. In the previous case, we connected the NMOS transistors in parallel, the PMOS in series. And for this case, we are conducting the NMOS transistors in series and the PMOS in parallel. And if we analyze, so how do we analyze such circuits? We basically analyze for all pairs of inputs. So in this case, there are 4 possible pairs of inputs. We just need to make a table of the form that I have shown of which transistor is on and which transistor is off. And then you'll quickly see that according to the design, the output will either get directly connected to the supply voltage, which will give it a logical 1, or get directly connected to the ground, which will assign it a logical 0. So here is a summary of logic gates, all our learning up till now that we have done. So we built all of these with basic transistors, with NMOS and PMOS transistors. So we can build we first built an inverter. So I'm starting from bottom up. So we first built an inverter that complements a single bit. Then we built a NAND gate. So how did we build a NAND gate? What we basically did is that we had NMOS and PMOS transistors, some in series and some in parallel. This is the symbol for a NAND gate. We also built a NOR gate. Sorry, I should add this. So we also built a NOR gate where we take A and B and we compute A NOR B. So so basically a NAND and a NOR are actually called universal gates in the sense that we can realize any logic function with only NAND gates and NOR gates. So the description of why this is the case is somewhat difficult, so I'll not discuss it now, but it should be kept in mind. So now we can easily construct an AND gate with at least all the basic gates that we have created. So what we can do is that we can take a regular NAND gate, add an inverter to it, then it becomes an AND gate. Similarly, we can create an OR gate. So what is the idea? We can take an OR gate that we have made with our transistors, then connect the output to an inverter. So we have A or B. So the symbol for an OR gate is like this. So the only difference between an AND gate symbol and an OR gate symbol is that in this case this line is straight and this line is curved, and also in an OR gate you can see an additional curvature, right? It looks like an arrow, right? Pretty much. So this is so these are called basic logic gates, and or NAND, NOR, and the inverter, of course, right? So let me maybe write an inverter over here. So these are called the basic set of logic gates that we have in our arsenal. And these basic logic gates we can use to build far more complex and complicated circuits. I'll discuss that in the next few lectures, but let's just keep this basic figure in mind that these are the basic logic gates that we have created from pretty much bare and simple transistors. Let us now discuss combinational logic. So what is combinational logic? It's essentially creating a complex logic function. So let me say what is a logic function. So logic function takes multiple Boolean variables as arguments and returns an output which is a Boolean variable, or it can return a series of outputs as well. So it can also return a set of Boolean variables b1 to bn, right? So this is made of logic gates, and so the final output is essentially one of the possible. So if let's say that there are n outputs, so there are 2 to the power n possible values. Some of these values are allowed and some are not allowed for a given set of inputs. So typically for a given set of inputs, only one value out of this set is allowed. So that's the reason we call it a combinational logic, where essentially we take a combination of Boolean bits and we determine the output. So let's first discuss, so what we want to do in this part is essentially discuss some of the most important combinational logic blocks that are used typically in modern processors, and the multiplexer is probably the most important logic block. So let's discuss that first. So mind you, in combinational logic we just take combinations of variables and then we decide the output. So there is no storage per se. So sorry. So let's consider a multiplexer. So in multiplexer we are given n inputs. We choose one of the inputs as the output based on the select bits. For example, if there are 8 inputs over here, then we'll choose one of the inputs, for example, let's say this input, to get reflected in the output based on the values of the select bits. So let's say this is input number 4, and if the values of the select bits are 1, 0, 0, then we'll choose this input to get reflected at the output. Similarly, if this is the last, if let's say the last one, the last line, we want the value of this to get reflected at the output, then the value of the select bit should be 1, 1, 1, right? Where we are assuming that they are numbered from 0 till 7. So this is a very important element in the design of processors. So we'll see why this is the case when we go to chapter 8, mainly chapter 8 and chapter 9. But nevertheless, let's try to understand how to actually build one such circuit to implement a multiplexer. So let's consider a 2-bit multiplexer where there are 4 inputs and there are 2 select bits, A and B. So if A and B are 0, 0, we want to choose the first input, 0, 1 the second input, 1, 0 the third input, and 1, 1 the fourth input. So what we do is that we generate all the combinations of the select bits, and so the 4 combinations are A bar and B bar, A and B bar. So B bar means the complement of B, and A complement ANDed with B, A bar dot B, and AB. So we are generating all the combinations of select bits. So only one of the combinations will actually be true for any value of A and B. For example, if A is 1 and B is 1, only this combination will be true. If A is 1 and B is 0, then only A dot B complement will be true. So only one of these combinations is true. So for this combination, so what we do is, the way we design the circuit is that we take each combination of the select bits, either the original bit or its complemented form, and we AND it with the input in an AND gate. Since only one of the combinations is true, the output of the rest of the AND gates will actually be 0. So let's assume that the output of this AND gate is 0, this is 0, and this is 0. And in this case, let's assume that this combination is equal to 1. So if x 1 0, if the input is 1, then the output is 1. If the input is 0, the output is 0. So in a sense, the output is reflecting the input if the select bits, so if let's say this particular combination over here is equal to 1. So since in this case the output is reflecting the input, this is x10. So let me explain this once again. Since a and b bar is equal to 1, pretty much their value does not matter. The output of the AND gate will be equal to whatever is the value of x10, right? Because what is the output? It's a, let me use the AND symbol, and sorry, is a and b bar and x10, which is equal to a and b bar x10. Since a and b bar in this case is 1, it's 1 and x10, which is equal to x of 10. So the output here will get reflected on the basis of the input. So now let's consider the OR gate that we have over here. Since all the rest of the values are 0, the output will also reflect the input, because anything odd with any Boolean variable, odd with 0 is the Boolean variable itself. So what we are effectively computing is x10 or 0 or 0 or 0. So 0 or 0 or 0, this entire thing is 0. So essentially this is x10 or 0, which is x10. So what we can see is that in this particular case where we are setting a dot, so in this particular case where a is 1 and b is 0, only this combination is true, the rest of the combinations are false. As a result, at this point the output is the same as the input, the chosen input x10, and similarly at the output of the OR gate, the output is equal to the chosen input. So for the entire circuit, the output is equal to the input that we chose, which is x10. So one more note regarding these equations, I could have used a different terminology as well. So typically for the AND operation, we'll typically use the dot operator. We might use the AND operator sometimes to make the explanation easy. We might write AND also to make the explanation easy. Similarly for OR, we would use the plus operator. We can use the OR operator, which is like a single vertical bar, or we can just write OR. So we'll use these symbols interchangeably depending upon the context, but the meaning is the same. So now coming back to a multiplexer, with the help of these equations, what we essentially showed is that depending upon the values of the select bits, only one combination is true, and for the input corresponding to that combination, it gets reflected at the output of the multiplexer. So on a whole, what do we have? What we have is that we have 4 inputs coming in and we have 2 select bits. Based on the value of the select bits, only one of the inputs gets reflected at the output. Alright, so now let's look at another structure called a decoder. So a decoder is very important. It is typically used in the design of on-chip memories. So in that sense, it's extremely crucial and vital to the design of processors. So what is a decoder? So decoder is also sometimes called a demultiplexer, but we'll use the word decoder in all our discussion. So what it means is like this, that given one input, let us make that input appear on one of the n outputs. So let's say we have one input, and in this case we have 4 outputs. So we want to make this input appear in any of the 4 outputs based on the values of the select bits a and b. In this case, the select bits are a and b. So let us assume that, let's say, the select bits are 1 and 0. So if the select bits are 1 and 0, so which means that A is 1 and B is 0. So we want it to appear on one of the outputs that corresponds to 1, 0. So let's see how does this work. So the way this works is very, very similar to the way that the multiplexer used to work. So in this case, we generate the 4 combinations for A and B, right? A bar dot B bar, A B bar, A bar B, and A B. Bar means complement. So then only one of the combinations is true. So in this case, which combination is true? A is 1. So A, this combination is true because A is 1 and B is 0. So 0 complement is 1. So 1 dot 1 is equal to 1. 1 and 1 is equal to 1. So this particular combination is true. The rest of the combinations are false. Since the rest of the combinations are false, the output that you get is 0, 0, and 0. For this case, if the input, let's consider the input to be x. So what are we getting? We are getting x ANDed with A, B bar. Using the distributive rule, using the associative rule, what we can do is we can replace this as this, right? Which is equal to x ANDed with 1, which is x. So what we can see is that if this combination is true, which is A and B complement, then the output at this point, which is essentially the second AND gate, the output of the second AND gate, which is chosen by the select bits, is equal to the input, which is x. So to summarize, what we have, essentially the decoder is a block where we have one input and we have 2 raised to the power n outputs, right? And we have n select bits. Based on the value of the select bits, only one of the outputs shows the value of the input. The rest of the outputs are set to 0. So we say that that particular output is enabled and the rest of the outputs are disabled. So this slide again summarizes the working of the decoder, which I'll just repeat. So the logic is the same as the multiplexer, which is generate all combinations of A, B, A complement and B complement. Only one of the combinations will be true. The output of that AND gate corresponding to that combination will be equal to x ANDed with 1, where x is the input, and x AND 1 is equal to x. And the outputs of the rest of the AND gates will be 0. Now, let us consider one more circuit called an encoder. So the encoder is also very important. It's also very useful in memories, particularly a certain kind of memories called content associative memories or CAM memories. So an encoder works like this, that given n inputs, assume that only one of them is 1, right? So this is a normal encoder. There's something called priority encoder, which I'll tell you what it is, but we'll not discuss its design. So let's assume there are n inputs and one of the inputs is equal to 1, the rest are 0. So then the output is, we'll find the ID of the input, that which input is 1, right? So for example, let's say that the inputs are numbered from 0 till 7. And the sixth input is equal to 1, the rest are 0. So output should indicate which particular input is 1. So the output should be 1, 1, 0, which is the binary for 6. So what happens when multiple inputs are 1? When multiple inputs are 1, we need to choose one of them based on the priority. So this is called a priority encoder. So priority encoders can be of many different types depending upon the priority. So we'll not discuss that. But readers who are interested in priority encoders can consult any of the classic texts on digital logic. So you'll find many different kinds of priority encoders. Let us look at designing a 3-bit encoder. So if I want to draw the circuit of encoder, this is what it would look like. I'm sorry, not a circuit, a high-level diagram. So I have, in the case of a 3-bit encoder, I have 8 inputs and I have 3 outputs. So one of the inputs is equal to 1 and I need to find out which input it is and then encode the number of that input in binary. So if you think about it, let the input bits be numbered B0 to B7 and let us consider the 3 output bits. So let's call them bit 2, bit 1 and bit 0. So as we can see, if bit 0 is equal to 1, the output needs to be 0, 0, 0. Similarly, for B1, the output needs to be 0, 0, 1. So essentially the binary encoding of 1. Similarly for B5, it will be 1, 0, 1 and B7, it will be 1, 1, 1. So what we can do is that for bit 2, we can write a Boolean equation to denote that when the bit is true, depending upon the values of the input bits. So let's use the plus symbol to stand for OR. So recall that we'll use plus for OR and dot for AND. So in this particular case, the second bit is equal to, because the second bit, when is it true? When either B4 or B5 or B6 or B7 is true. So this is the logical expression for when bit 2 is true. Similarly, if we take a look at bit 1, when is it true? It is true when B2 and B3, sorry, B2 or B3 are 1, or B6 or B7 are 1. So we can say it is B2 or B3 or B6 or B7. That is when bit 1 is 1. In the rest of the cases, the default prevails, which is 0. Similarly, for bit 0, so bit 0 denotes the unit, the least significant position of the binary number. So bit 0 is true if either B1 is true or B3 is true or B5 or B7. So this is the Boolean equation of bit 0. So all that we need to do is that the Boolean equations that we have over here, we need to implement them with logic gates and we are all done. And for a 4-bit or a 5-bit encoder, the logic will change in a similar manner. So we need to make a table as shown over here. So we may need to make this table once again. And for each output bit, we need to find out for which inputs it's set to 1, write appropriate Boolean equations and implement them. So let's consider the circuit of a 3-bit encoder. It just has 3 OR gates. And so if you see the equations here show that we are taking an OR of 4 quantities of 4 bits. So each OR gate has 4 inputs and the inputs vary depending upon which output bit it corresponds to. So bit 2 is B4 or B5 or B6 or B7. Similarly, bit 1 and bit 0, the circuits are determined by the equations on the previous slide. So this is a fairly simple circuit. All that we need is 3 4 input OR gates. So a 4-bit and a 5-bit encoder are slightly more complicated in the sense we need OR gates with even more inputs. But this is the basic idea. Subsequently, we'll take a look at sequential logic. So that will be there in the next lecture. So in the next lecture, the idea is to cover sequential logic and memory cells.